Hi guys. Okay. I'm going to start going over the paper one content. I've been through the specification and I've come up with bits and bobs which I think either you may have forgotten or stuff that I think is going to be possibly on the exam this year. Okay. So I'm just going to start from the very beginning. We're going to have a look at energy. I'm going to see how much I get through. I'll just go through a topic at a time. It's not going to be a total overview of the topic, but I'm just going to dip into bits and bobs, hopefully bring up things which you might not have thought about before. Okay. Um, okay, let me share my screen. Yes, bear with me. I'm full of cold. All right, so what we're going to start with then, guys, is energy. Let's just come up with a few of the equations. I know you get given the equations, but it's a good point to start and think. Then you can sort of build the topic around those equations. So we've got kinetic energy equals half times mass times velocity squared. We've got gravitational potential energy is mass times gravity times height. We've got elastic potential energy equals half ke squared. What else have we got? Energy equations. Blimey, head's come blank. What else have we got? Energy. I've got a data sheet. Let me go get a data sheet. Oh yeah, of course. We've got efficiency equation as well. So efficiency equals useful energy over the total energy that went in times by 100. You've got your power equations in there as well. So we've got power equals energy divided by time. That sort of goes through the whole topic, really. That power can come up in electricity as well, actually. So although there's an electricity version, which is power equals current times by voltage, isn't there? And the other one that could come up in this topic as well, which is also in the third topic, is the specific heat capacity equation, which is change in energy is mass times specific heat capacity times by change in temperature. So there's all my equations. We'll dip in and out of these as they crop up. What I want to remind you guys is, especially with these three here, you've got lots of different types of energy. For example, I can split them into stores and transfers. Now, this is definitely worth going over because it can be a little bit confusing for some people. The way in which I remember the types of energy that can be stored is kg of cement. Okay, and so this is kinetic, this is gravitational potential energy, this is chemical, this is elastic, this is magnetic, electrostatic. Notice how that's not electricity. You can't keep electricity in one place. You can't store it. It has to just keep moving all the time. And then nuclear and thermal. So, for example, if I have an object up high, it's got gravitational potential energy. If I've got an object that's moving, then that's going to be kinetic energy. If it's continuously doing that, imagine like a swing, it just keeps swinging, then it's stored. That energy just stays there. But then eventually the swing will stop, and that's because of a transfer. Something's been transferred from one type to another. Now, remember, we can transfer from one type to another type to another type to another type. And thank goodness we can, because otherwise we wouldn't create electrical energy, for example, that we need in a power station. But let's look at the transfers before I go any further. The transfers I'm going to do a different color. I use Herm to remember this. And the way in which energy can move out of the stores or between the stores is heating, electrically, radiation, which, by the way, is sound and light. Remember, guys, if you know this bit, by the way, just fast forward, okay, to the next bit. Mechanical. All right. So, for example, I have an object that's up high. It has gravitational potential energy. As soon as it starts to fall, it's the change that makes that happen is a mechanical force. It's gravity that's bringing it down. So what happens here is if I was to write this out, I've got kinetic start, and then I'll do in a different color the transfer, and I'll put it in a box as well. And the transfer that happens is mechanical. Okay, but then it changes. Oh, I've done it wrong. Sorry, guys. It started off as GPE, didn't it? Not kinetic. So GPE. Then, so it's up high, it's got GPE. Then a mechanical force of gravity made it change into kinetic. And then it hits the ground. And when it hits the ground, it's going to dissipate, isn't it? Because it doesn't, unless it bounces. But that energy then is going to dissipate. And and usually we get a bit of sound, but we also get a bit of heating. So there's probably two ways in which it's transferred here. So I'm going to put heating for the friction when it hits the ground, but also a little bit of sound, which is radiation when it hits the ground. Okay, and then that gets dissipated to the rest of the surroundings then. Dissipated, the word dissipated means lost to the surroundings. Okay, so here I had a store, and here I had a store. So this one's taken me from store to store, but then I've lost it to the surroundings at the end of this because all the energy's gone. So could I call this a closed system? No, okay, because if it keeps going from store to store to store to store to store and you don't lose any, then it's a closed system. If you can kind of put the situation in a box like this, and if all the energy stays in the box, okay, whatever the situation is, then it's a closed system. But if it gets lost to the surroundings and out, then it's not a closed system. Now, let's have a look back at these. Stores, you can keep them all in one place. Okay, the transfers are the ways in which it's lost from the store or that it moves between the stores. Most of the time it's mechanical that makes it happen. But to give you another scenario, if I have a hot cup of coffee, okay, it's going to have inside of there a store of thermal energy. You look at my stores up here, thermal energy. And then what's going to happen is there's going to be some sort of transfer. And that transfer, if I go to the transfers, is heating. It's going to be lost to the surroundings in that way, isn't it? So the heating is the transfer. And what happens is it just gets lost to the surroundings like this. Is this a closed system? No. Okay. So only when the energy sort of stays in and you don't lose any energy, then it's a closed system. Okay. Now, of course, in everyday life, in lots of situations, we're trying to avoid unwanted energy transformations. So if I look at a power plant, for example, we start off with a furnace, and then the furnace heats up water pipes over the top, and then the water turns to steam, and that turns a turbine, and then the turbine spins inside of a generator, which is a huge magnet. Okay. This is my generator. And then out comes electrical energy out the other side, and it carry on with the power station, etc. But let's have a look at the energy transformations. We've got, first of all, what went into here. Well, it depends, actually. This could be coal, for example. Coal goes in, so that's chemical. That's an energy store, isn't it? And then the next energy store, there's transfers that happen, by the way, in between these, but I'm not going to draw those on at the moment, is heating, is thermal. And then the next store we end up with, well, this thermal energy turns the water into steam, and the steam moves, so it's kinetic energy. And then that, let's just move this out of the way. And then that spins inside of here, and it creates electrical energy. And actually, electrical energy is a transfer, because you don't store it. Okay, it just keeps moving all the time. But of course, there's transfers that are happening in between here as well in order for them to move to the next step. So these are wanted transfers, but an unwanted transfer in the situation, for example, might be, imagine losing heat energy from this pipe. Okay, what could I do? I could fix that by putting some insulation around it. Okay, to stop that heat energy being lost, I could put insulation around all of this in order to keep the heat energy in. If I lose it, it's unwanted. I want electrical energy out of the end of this. So you've got to, you've got to avoid unwanted energy transformations. But what's the word that we have to attach to that, guys, is efficiency. Okay, I would increase the efficiency of this system by insulating it. And what is efficiency? We want to make sure that we reduce the amount of wasted energy. So reduce wasted energy. Okay, and this takes me to my efficiency equation, doesn't it, here? It's the useful divided by the total energy that went in times by 100. Okay, so that's a nice little equation you can apply to anything with regards to efficiency. But what are we trying to do? We're trying to avoid unwanted energy transformations from happening. Another way we can think about this as well is, imagine if you had an engine, and inside the engine you wanted to avoid friction. So friction, guys, often takes something like kinetic energy, which I'm going to put as EK, kinetic energy. And in a car, you want to maintain the kinetic energy. But if there's friction between the parts in the car, then you end up losing that kinetic energy as heat, for example, or sound. And you don't want to lose any of it. You want to keep that kinetic energy. You want the wheels to keep turning because the engine's making that happen. So how do we reduce that? This is something that's in the actual mark scheme, in the spec now, guys. And I wondered if everyone would say this. You have to use lubrication. So actually physically say that word. So reducing unwanted energy transformations due to friction. Okay, you need to use lubrication. An example of that in a car would be oil, but you would say lubrication, you would then use the example of oil, but make sure you say that word. It's really important. Okay. All right, something else that came up in the spec, which I was unsure how confident you were on, is I wanted to talk about heat transfer. Because, yeah, we can have a thermal store, but actually heating is a transfer as well up here. So if I go back up here, heating is a transfer too. So there's 3 ways in which heat is transferred. Okay, and we've done this before, but let's just double check. Conduction, convection, and radiation. Okay, now conduction happens in solids, and it's basically if I had 2 solids touching like this, all the particles in a solid are all touching together like this, aren't they? And what can happen is that if this starts to get hot, it passes it on particle to particle. Okay, so it only happens when the particles are close together in a solid, and that's how the heat moves through the solid. So that's conduction. Another way is convection, and convection is when it creates a current, a circular current like this. So, for example, in the UK, you have radiators on the wall and they give out heat, and the heat rises because it becomes less dense. If you think about the particles in the air, if you heat it up, they're going to move apart from one another because they've got more kinetic energy. Okay, so the more kinetic energy they have, the further apart they get. And the further apart they get, they get less dense. Because if they're tightly packed like this, it means that they're dense. But if they're like this, these are less dense. So, of course, that air will then rise, and then it travels along the ceiling, and then it gets cooler, and then it drops. It becomes more dense, and it creates this circle like that. So that's convection. Guys, this happens in fluids. When I say fluids, I mean liquids and gases. If you ever see fluids, that's what it means. It means fluids. It means liquids and gases, not just liquids. Okay, because the particles need to be able to move in order for this to happen, so you can't happen in solids, the convection current. And then radiation is the last one. Like with my cup of coffee before, okay, if it has a thermal store like this, it's going to end up giving out infrared waves in every direction, okay? And it's a wave. It's an electromagnetic wave, and it can travel through a vacuum. So this is how the heat from the sun gets to us. And it's not heating up space, is it? Because there's nothing in space, but when it hits an object, it then starts to heat up that object. Whilst we're on infrared, actually, let me talk about this in a bit more detail as well. Please remember that if you have the Earth, which is here, and then you have the atmosphere over the top of the Earth, and then up here I have the sun. There's three different waves that come from the sun. You've got UV, you've got visible light, and you've got infrared. And they all come out towards here. Now, let's just look at the infrared for a second. The infrared will have a heating effect. This is more paper two, really, to be honest, but I just want to make sure that we're touching on it whilst I'm saying it. It will go through the atmosphere and it will heat up the Earth. But then what will happen is the Earth gives out its own infrared. Yes, you get a little bit of reflection happening. Okay, you get a little bit of reflection of that wave off there. But actually what's happening is the Earth is heating up. It's getting its own thermal store of energy. And then it's giving out its own infrared back into space. And of course, global warming and everything else fills this atmosphere with carbon dioxide. And that makes it harder for the infrared to get out, and hence why we have global warming. Anything else to say about that? Oh, yeah. There's another question about how does an object maintain a constant temperature? So, for example, in the daytime, the Earth, imagine you're, I don't know, here in Dubai, it keeps a constant temperature of probably about 40 degrees in the day. And how does it maintain that constant temperature? Because you've got the energy in and then you've got the energy out. Okay, so energy coming in, energy going out. And that's how you maintain a constant temperature, is that the energy in equals the energy out. That's what you would say. How do I keep a constant temperature? So when the energy in equals the energy out. Okay. What else do I need to say? Okay. There's this term, thermal conductivity. Imagine copper. It's a metal. It's a very good conductor. I think that they're going to go to town on this thermal conductivity as well. Some mark schemes, even if you describe copper as saying the heat transfers through it really well, or whatever you want to say, if you don't say thermal conductivity, you're not getting the marks. So you know how I taught you to have a bit of a crib sheet on the side, like an A3 sheet of things that you mustn't forget to say? I want you to put that word, thermal conductivity. Okay, that means that the heat travels through something really well, but I need you to use it because sometimes in mark schemes, they won't give you the mark unless you've said it. Okay, the physics exam is very much like this, isn't it? About the language you use. Make sure that you put that on your crib sheet for me. So it says on here on the spec, I'll read it to you. The higher the thermal conductivity of a material, the higher the rate of energy transfer by conduction across the material. So it transfers the energy faster. Students should be able to describe how the rate of cooling of a building is affected by the thickness and the thermal conductivity of its walls. So, you know, like the insulation on the inside, you know, like on houses in the UK, they're insulated. And the thermal conductivity is low in that insulation because we don't want the heat to be lost. That is I'm making a prediction there that something about thermal conductivity is going to come up in your exam. Okay. Right. I just wanted to double check as well, because the second half of the energy topic goes into fuels and the environment and the national grid and energy resources. And I just wanted to make sure that people knew about which fossil fuels there are. So coal, oil, and gas. And of course, these are non-renewable. And then you have your renewable types. There's actually 7 of those that you can mention. So you've got biomass, you've got solar, you've got wind, wave, hydroelectric, I always miss some of them. Tidal, geothermal. How many have I got? I think that's it. I should have times 7 of those. And these are renewable. You need to have an idea about some positives to do with these, and there's things that you can say every time. And I've found sometimes that when talking about these, you feel like you're repeating yourself in questions, but they all have the same benefit in the fact that they don't create carbon dioxide. Okay, so they don't create carbon dioxide when they're not burnt. There's no carbon monoxide, and but then you might have to talk about their reliability. Reliability of a source is really important comment to make, because the reason why we don't always go for all these renewable energies is because they're not reliable in certain situations. For example, wind. We wouldn't choose wind here because it's not always windy. Remember, you've got to state the obvious in some cases, but yeah, definitely say the benefits of them: no carbon dioxide, no carbon monoxide, no global warming. Okay, that's the benefit to all of them. And then these fuels, of course, the coal, oil, and gas, they're going to run out. They're non-renewable. They create carbon dioxide. They create carbon monoxide. They create global warming. Right, I just want to read this comment out on the spec here, which I don't think has ever really come up. But I just want you to have maybe a glance into this. Show that science has an ability to identify environmental issues arising from the use of energy resources, but not always the power to deal with the issues because of political, social, ethical, and economic considerations. I think a lot of that's going to come down to your common sense, to be honest. You know, like, why might it affect the economy? You know, do these cost a lot of money, for example, to set up, like wind turbines cost a fortune, and is there the space economically as well, and social, how much space is it going to take up, and is there going to be enough land to build houses for people, There's all sorts of things you can look into on that one. Okay. So one last thing I wanted to remind you of is, if I go back up to my energy stores here, guys, there's typical questions which could come up, and you've probably seen them all before, is like, for example, there was a spring one, wasn't it? And the spring had been stretched and it started off having elastic potential energy. And then it was let go of and it was released, and that turned into kinetic energy. And then it turns into gravitational potential energy the higher it's getting. So I just want to show you that you can go from having this energy to that energy to that energy. But if this was 10 joules, this will be 10 joules. This will be 10 joules. In reality, you do lose some because of air resistance, because of friction, because of unwanted energy transformations. But a lot of the time it says ignoring air resistance or such things. But if I wanted to calculate elastic potential energy, I do half KE squared, for example. There's two of these, by the way. There's half FE squared as well. Sorry, half KE squared. All right. That doesn't seem right. What's wrong with me? Yeah, that's why. That one's right. It's half FE, not half FE squared. I knew it said something wrong. If it's half KE squared, for example, the kinetic energy is half mv squared, and then the GP is mass times gravity times height. It means that all three of those equal each other. So you could actually write them out like that. Equals half mv squared equals mgh. Okay, because that's 10, that's 10. So if ever you need to work out, for example, you might want to work out the speed, and you have K and you have E, and it asks you to work out the speed. Well, you just ignore that bit then, and then you've just got to rearrange it. So it becomes half KE squared. And then if I'm going to get rid of this from this side because I want this on its own, then it becomes half M under there, and they cancel out. Look, half and half will cancel out each other out because it's top and the bottom. And then it becomes that equals V squared. And of course, then you need to root this side to get rid of the squared. Because you can see that if you wanted to work something out that you didn't have, you could. Okay. So I think I've touched on energy quite well there. Energy, it's ingrained in everything. So you need to have a real good handle on that one. So just make sure that you know it well. Right, I'm going to move on to electricity now. See how far I can get through this. I know someone's coming into my room soon, so I might have to stop soon and then I'll start another one. Okay, so the next one is electricity. Right, some common circuit symbols which people often get wrong. Let's start with those. I won't do the easy ones. I'm just going to do the ones which people get wrong. So this one here, a fuse. This one here, a thermistor. This one, an LDR. What have they all got in common? Look at them. They all have like an oblong box in the middle of them. So they're all types of resistors. An LDR though, what I have missed off though here, guys, it's a light dependent resistor. So I need some arrows of light coming in like this, don't I? Okay, another one, let's have a look. A light emitting diode, for example. This is a diode, like the triangular one, like that, like an arrow. And it's a light emitting, so the light is coming out. So this is a light emitting diode, LED. Those are the most common errors I think that people get wrong. The only other thing I want to say is if I have a cell like this, and then if I end up with lots of cells together where it does 1, 2, 3, like that. Sorry, get rid of that on the end there. Make that into a line. So I've got 1, 2, 3 cells together. So if this one said it was 1.5 volts, I've got to do 1.5, add 1.5, add 1.5, and that gives me the total voltage there. So you can add cells together like that, can't you? Now, drawing circuits, you might be asked to draw a circuit. I want you to do it with a ruler and a pencil. You might be asked to, I don't know, draw something, a few components in the right places. Remember, your voltmeter goes over the top of the component in parallel, and then your ammeters always go in series. So draw them carefully. Make sure that you have straight lines with a ruler. Another one I want to talk about is this one. Let's just get rid of the line for the middle because I don't want to do a fuse, but I do want to do this one. So this is a variable resistor. Now, often what we do is we put these in circuits when we need to control the current. So imagine current is my independent variable in an investigation. And I need to say, imagine in my table, it's like the current in amps. And then I need to go to 0.1, then 0.2, and then 0.3. It's very hard on its own to just get those readings. Exactly 0.1, exactly 0.2. So we would use a variable resistor in order to control the current, in order to get it how we want to get it. So it changes the resistance, doesn't it? So we can just play around with that until it hits exactly 0.1 and then we can test it. So that's why we would put a variable resistor in a circuit. For example, when we're doing current voltage, you know, the IV graphs practical. IV graphs, by the way, I'm doing a separate video on all the practicals at a later date, so I'll talk through those with you. The IV graphs practical, we would use a variable resistor in order to get the current set to how we want it, and then we would take measurements of voltage over the component. So that's my components sorted. Let's just talk through some of the equations as well, actually, guys. I've done some components there, but we've got V equals I times R. We've got E equals QV. That's a hard one, that one to remember. Lots of people forget about that one. We'll talk through that one in a little bit of detail. What else have I got? This topic's the one which has got the most equations in, isn't it? We've got charge equals current times time. We've got our power equations here again, haven't we? E over T, and power equals current times by voltage. What else have we got? Oh, power equals current squared times R as well. And then we've got our resistors in series and parallel. Let's have a look. So resistance total equals resistor 1 plus resistor 2 etc., etc. But if they're in parallel, it's 1 over resistance total equals 1 over resistor 1 plus 1 over resistor 2, etc., etc., etc. This bit is not for combined. Okay, so don't worry about that. Sorry guys, I can't breathe. So those are our equations. What else I want to talk to you about with this one? Oh, I wanted to talk to you about two particular components and how current, and remind you about how current and voltage behaves in different circuits. So if I have a circuit like this, I don't like the way it's done. Right, if I have a circuit like this, and I have an ammeter here, and then I have a lamp and a lamp. Sorry about the roughness of this. Voltmeters go over the top of the lamps like this, don't they? If it's a series circuit, if I put an ammeter here and an ammeter here, imagine this reads 2 amps. This one is also going to read 2 amps. Guys, remember that current is like people in corridors. Okay? If I have 2 people here, I'm going to have 2 people here. Okay, that's not going to change. You can't cut people in half. You can't, they don't disappear randomly. The current in a series circuit stays the same. If this is 12 volts on the top here, this is going to be 6 volts and this is going to be 6 volts if it's evenly split. But it can't be more than 6 and 6 because that doesn't equal 12. Everything on there has to equal, each branch has to equal that 12 volts that's at the top. So let's have a look at a parallel circuit now. 1, 2, and then we'll just put 1 down here. And let's put my ammeter, 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 and then a voltmeter, voltmeter, voltmeter. Okay, so imagine this reads 6 amps and this reads 6 amps, okay? Because of course, when it comes back round, it's like people in corridors. It doesn't matter which corridor they go down here, they're all going to come back over here. So that's going to be 6 and 6. I know that this is 12 volts. So remember that this, I'll write in red so you can see where I'm writing over the top. This, if it splits evenly, that's going to be 6, that's going to be 6. This one though, because there's only 1 on the branch, it means that's going to be 12. And let's have a look here. I have here 6. And imagine I've got 6 people coming down this corridor here. It's got an option of this way and this way. Which corridor are you most likely to go down? Here, there's 2 obstructions, and here there's 1 obstruction. So you're most likely to go down this corridor here, aren't you? Because there's less obstruction. So the larger proportion of the 6 is going to go down there, and the rest is going to go down here. So really, I need to split this into 3 parts, and 2/3 is going to go down this one, and 1/3 is going to go down here. So I'm going to get the majority of the current going down here, and then the rest is going to go down here. So 2/3 of the current is going to go down here because there's less on it, and then 1/3 is going to go down this branch here. Okay. What was I going to say? Yeah, so 4 and 2, for example, would be my split of the current, but then it's all going to come back together and you're going to get 6 over here. What was I going to say? What's the next thing? Oh, another tricky thing with a circuit is this. Imagine I've got 2 resistors like this. Okay, I know that the voltage over each of these has to equal whatever's at the top. Let's say it's 12 volts again. Let's keep it simple. So that would be 6 and 6. Now, what would happen if I increase the resistance on this resistor? This is a common thing that stumps people. Basically, what's going to happen is if I increase the resistance, it's going to be harder for the electrons to move through. So I'm going to get a buildup of electrons on one side. Now, remember that voltage, guys, which is here at the bottom, this voltage, another way to write it is potential difference, PD. And what it means is the difference from one side to the other side. So the potential difference here, if I increase the resistance, the potential difference is going to go up because from one side to the other is a bigger difference. So here, I'm going to change this to 8. So tell me, what's going to happen to the potential difference over this one if that's 8? Well, look, it has to equal 12. So that's going to go down to 4. Okay, so increasing the resistance actually increases the potential difference. So if I increase the resistance here, I'm going to increase the potential difference over this one, but actually decrease the potential difference over this one. So, but what happens to the current? If I put an ammeter here and an ammeter here, and now that I've actually increased the resistance, guys, the current stays the same. Okay, because it's series, the current is the same everywhere, and it doesn't matter what you do with all these resistances, the current stays the same. Okay, that's a common problem this here. Have a look at some examples of those in exam papers and have a go at them. Next, I want to talk to you about an LDR, specifically a light-dependent resistor. That's supposed to be a rectangle. In comes light. I want to talk to you about the patterns because this is controlled by light. If I put it in a circuit, it will control my circuit in a particular way. But what happens with the light intensity? So if I increase the light intensity and then decrease the light intensity, how will this affect the resistance in the circuit? So, for example, going back to this could be here, this one that I drew in for, that could be an LDR. And it could be the light controlling the resistance on it. So light intensity is this. If I increase light intensity, it has high resistance in the dark and low resistance in the light. So my resistance goes down. So low in the light. Okay, L and L, low in the light. But then it's got high resistance in the dark. Okay, so I'll put high in the dark actually there. Okay, so it's got high resistance in the dark. Okay, that you need to remember. I think as a prediction that they're going to bring something up that you need to know those how that behaves. Now, another one is the thermistor. Again, I could have replaced that component with the thermistor instead. That is terrible. Don't draw thermistors like that. Remember, when you're drawing circuit components, you draw them with a ruler and pencil and make sure they're spot on. I've seen this drawn so many different ways. Be very careful. It has to be exactly like this. It's a flat line and then it goes up. No arrow at the top or anything like that. Okay, just exactly like that. This is controlled by temperature. So I could have put this in my circuit and let the temperature control it. So if I increase the temperature or decrease the temperature, it's going to affect my resistance. Increasing the temperature, you would think, causes an increase in resistance. Actually, it's the opposite. It decreases the resistance. So it's a bit of a weird one. I want you to think of this as the strange one. You'd expect an increase in temperature to cause an increase in resistance, which, by the way, in every other situation, it does. However, this has something called a negative temperature coefficient. Sorry, can't write very well here. Negative temperature coefficient, which means that when the temperature increases, the resistance goes down. And so when the temperature decreases, the resistance goes up. Okay, so make sure you know examples as well of where those used. For example, this might be used in a thermostat. It might be used in what else? It might be used in AC, for example. You know, when you put it on what's it called? Auto, and it reads the temperature in the room and then changes the circuit according to the temperature. It might be in an AC unit. Right. What else did I want to do on electricity? Right, there's a few more things. I'm just going to pause there and I'm going to start the next video in another room because I think someone's coming in to use my room here now. So I've done 40 minutes. I'll carry on with electricity in my next video. Okay, guys, hope it's helpful. Make sure you're doing lots of practice questions and yeah, I'll come back at you with the next video. Okay, bye guys.